introduction, I would like to warmly thank the organizer for the invitation to this CEFIPRA-sponsored symposium, and it's a great pleasure to be back in India after 6 years, so that was before the pandemic, and to meet again good friends, so it has been a long while, so it's pretty cool. So today I'm going to talk about photocatalytic and electromediated borylation and silylation reaction. So just before starting, I would just like to emphasize a little bit on our research program. So at the beginning, we worked a lot on organofluorine chemistry, but we drastically changed our way of doing research. And we are mainly focusing currently on copper chemistry, photochemistry. We started also electrochemistry, and just during the pandemic, we started a continuous flow synthetic program, and we dedicated a lot of efforts to synthesize very important API. So here is some name of API that you can just Google and get the structure, so we synthesize them. But today I will mainly focus my talk on copper photocatalysis and electrochemistry. So why did we start with copper chemistry? So actually this is an industrially driven research. So we had a collaboration with this company with mainly focusing on API synthesis, and they came to us and they asked us, we need a methodology to carry out a mirror borylation reaction on aryl iodide, bromide, vinyl iodide to get access to this BPIN compound. So that was the request from the company. We want a copper-based photocatalyst because copper is very cheap. We need to use visible light, high direction condition, high functional group tolerance, and of course an extension to flow to carry out the scale-up of the reaction. So that was the request at the beginning, so we worked a lot. So basically Antoine did it, and we designed some copper complex. So this is the best complex from the literature that we screened, and it gave us 52% yield. And to fulfill the requirement of the contract with the company, we developed this catalyst with a guanidine-based NN ligand, and we got a better yield. So this complex was really made for this reaction. And here are the properties of the complex. So we have the redox potential, absorption, emission. We also determined the potential at the excited state. So it was fully characterized. Unfortunately, we never got access to the crystals, so that was a pity, but so far that was okay. So here are the conditions. So we changed a little bit from the previous slide. We have to use the IPA as a sacrificial reductant, a little bit of pyridine to activate the B2-pin2 in order to facilitate the radical addition, blue LED under drastic condition under argon. And here is the scope, so I will not go that much into details, but what is important is the functional group tolerance that you can see here. Most of the functional group were well tolerated, and yields were pretty good. We extended the reaction to aryl bromide, but we cheated a little bit because we have to use electron withdrawing group to decrease to increase the oxidation, to decrease the reduction potential. Sorry, we carried out the reaction of vinyl iodide, and some alkyl iodide were also suitable substrate. So, as requested, we also developed the flow condition. So, using this Vaportec photo reactor, and we carried out the reaction up to 5 grams. So it's just a proof of concept. We never optimized, but the company took the technology and it's now implemented on routine. So then we wanted to develop more academic research, and we were wondering, could we develop some kind of photocatalytic hydroboration reaction using quite a similar complex? So we wanted to develop photocatalytic hydroboration reaction. So Ming Bing worked on this project, and actually we wanted to get access to boryl radicals. So in 2020, boryl radicals were not that popular in synthetic chemistry, and the main radical that you can find is a neutral boryl radical, so which is a 5-electron one. It's pretty rare, some kind of curiosity. It's not synthetically useful, but the most important one is the ligated one, the 7-electron, which is easier to form and which might have an interest in inorganic synthesis. And to get access to this radical, you might do hydrogen abstraction on the borohydride, or you can cleave a BB bond to get access to this boryl radical. So this is the last strategy that we investigated. So here are some selected reports that were published during that time. So the concept was an oxidative strategy. So we wanted to form a radical from B2-pin2, but first we wanted to get access to this borate, which is well known. This is intermediated in the mirror borylation reaction. And then upon an oxidation, we hypothesize that the possible fragmentation might give birth to this boryl radical, which might be used as a synthetic radical, as a synthetically useful radical. So first we carried out some CV analysis, and in green, so this is a B2Pin2, so we might not witness any oxidation, but as soon as you had potassium hydroxide 1-to-1 with B2Pin2, you might see here an oxidation potential around 0.25. So this is some kind of proof of concept that we can oxidize this species, but then the most difficult part is to try to do something with it. So to make a very long story short, we developed the hydroboration on alkyne, terminal alkyne, internal alkyne, and also alkene. And we had to develop our own catalyst, so copper-based photocatalysis. So we tuned the structure. Here it's a phosphoramide. Here this is the N-xanthos. And basically, using mostly the same reaction condition, we got excellent lead for the terminal alkyne, moderate selectivity for the internal alkyne, and excellent reactivity for the styrene. So that was a good proof of concept. So we developed the scope of this transformation. So for the terminal alkyne, you might see some examples. So yields are pretty good, whatever the substitution pattern. So I will not go that much into detail. We were also able to use more fancy compounds, so pyridine, thiophene, enine, alkyl derivatives. Some iodide were tolerated without any reduction, so it really proved that we are working under oxidative condition. Alcohol were also well tolerated. We did it on internal alkyne, so we have less examples, so the reaction was a little bit tedious, but it worked. We also extended the reaction to bidan by using a mixed bipene-bidan compound, so we might easily transfer the bidan versus the bipene, but this is well known. So for the alkene, here are the scope. It's also pretty good. So we did some styrene, aliphatic compounds, more fancy complex, and also some Michael acceptor gave rise to the beta-borylated compound. So then the most interesting part was the study of this mechanism. So we wanted to know if it's a real photocatalytic reaction. So we measured the quantum yield of this reaction, and you might see it's always below 1. But the values in some cases are pretty high, 0.48. So it might involve some short radical chain in the process. So that was a bit puzzling. So I would talk about that a little bit later. So short life chain might probably involved in this reaction. The main question was, where does the hydrogen come from? Because this is not an hydride. You get a formal hydroboration without an hydride. So we carried out some labeling experiments. So here are the results with normal acetonitrile in water, 81%, of course 100% of hydrogen insertion. When we use CD3CN, we transferred only the hydrogen. So that was a bit puzzling. And when we used deuterated water, we incorporated the deuterium. But if you have a look to the BDE of the solvents with water, 119 kcal, acetonitrile 92 kcal. So if it's a hydrogen transfer, it should come from acetonitrile, but not from water. So that was quite puzzling at the time. So we also imagined that a boron species might be involved in the hydrogen transfer. So we carried out some kinetic experiments. So here is the reaction with deuterated water, with normal water. So this is the standard condition. With deuterated water, we have a KE effect. But when we added some boron compound in the reaction media, we have an increase of the reaction rate. So boron species might be involved in the hydrogen transfer. So for similar observations, there are these references. So the KE was around 5.5, so it means that the hydrogen transfer was probably the rate determining. So here's the suggested mechanism. So I will go quickly on it. We did some calculation with Mathieu Frenette at the UQAM. So it starts from the borate. We have an oxidation to generate this boryl radical, which quickly this radical which quickly collapsed into the boryl radical, and the addition was calculated to be extremely fast. And then we have two possible pathways: a reduction and the proton abstraction, which is likely with the incorporation of the hydrogen from water, but this is probably not the main pathway. What we can imagine is a hydrogen transfer from the borate radical to regenerate this species. So this is something that we imagine, but currently we think that this boron can coordinate the water, and we might get an intramolecular hydrogen transfer with water, which can also explain the selectivity of the hydroboration which is seen. If it's a real radical process, it should be anti. So this is probably what happened. So this is a photocatalytic cycle and mostly the radical chain pathway. But then we wanted to extend this strategy to other radicals, and of course we investigated the suginome reagents, so the bipinsilane, and upon the same strategy, borate formation, oxidation, fragmentation, we might get access to the silyl radical. So CV experiment says that it's possible to do it. So when we mix the suginome reagent with potassium hydroxide, we might see also an oxidation wave, which is pretty low. So we carried out the reaction, and what was surprising for this reaction, flow conditions were mandatory to get excellent yields. When we carried out the reaction in batch, we never get up to 40% yield. So with flow chemistry, we got almost quantitative yields. So we developed also another photocatalyst, so I forget to have the structure, so sorry, but if you're interested, I can show it to you later. So here are the scope of the reaction. We have a good functional group tolerance on aromatic alkyne. We carried out the reaction on more fancy substrate as well, and yields were okay. In some case, we have branch and linear mixture, and also easy mixture in the case of the alkyl substituted substrate. The olefin also were a suitable substrate, so here are the scope. I will not go that much into detail. So then we started the program on electrochemistry, and I don't have to convince you, but electrochemistry, the electricity is produced from green and sustainable resources. It's a good tool to develop green chemistry, and actually it has been recognized by UPAC and the UN as an excellent technology for getting access to sustainable chemistry. So this is the way I can justify this research program, but actually it's pretty true, and it's a top priority defined by UPAC. So these two guys carried out the electrification of hydroboration hydrosilylation. So we developed some condition by using stainless steel electrodes. Of course, we have to use an electrolyte for conductivity. We used a current of 10 milliamp and 2 Faraday per mole. So 2 Faraday, it's basically the stoichiometry in electrons. So 1 Faraday means 1 equivalence, 2 Faraday means 2 equivalence. We use methanol, and upon this reaction condition, we carried out the hydroboration. The substitution patterns tolerated are demonstrated here, so yields are pretty okay. We also did it on fancy substrates, the cyclopropane. I do like it very much, even if the yield is a little bit, the isolated yield is a little bit low. This is a very nice example. Free alcohol were tolerated. We didn't have over-oxidation. We got also access to complex substrate, so that was a pretty nice reaction. Likewise, in the previous project, we carried out some labeling experiment, and as you might see, the deuterium is coming from the OH, the hydrogen is coming from the OH and not from the CH3 of methanol, which is also unlikely because BDE is less energetic with this CH bond than the OH bond, so this is quite strange. But the real proton is, the hydrogen is coming from the OH as demonstrated here, so which is almost the same observations than in the photochemical process. So we demonstrated also that this is a rate determining step, so this is a parallel experiment, the KI is 2, but when we mixed methanol and fully deuterated methanol, we got almost 6 of KI, so this is really the rate determining step. So here is the CV of the reaction mixture, so the most interesting is the blue one. When we mix B2Pin2 and sodium methoxide with phenylacetylene, we might observe this oxidation wave just below 1. Why did we use sodium methoxide? Because we think that sodium methoxide is generated at the beginning of the reaction at the cathode. So by reduction of the solvent, we generate methoxide, which might activate the B2Pin2 and then can promote the formation of the boron radical. So here are the oxidation waves, and here is the suggested mechanism. So basically it starts as a cathode by the generation of methoxide. We form the borate with B2Pin2, and then at the anode we have the oxidation, formation of this radical which collapse into the boryl radical, and then we have a quick addition onto the alkyne, and then hydrogen insertion here on this radical to form the hydroboration product. We did the same with silylation. The mechanism is the same: borate formation, oxidation, formation of the silyl radical, addition, and hydrogen atom transfer. So that was exactly the same. Here is the scope. Conditions were a little bit different. We changed the electrolyte, but we have to use acetonitrile as a co-solvent. Otherwise, we have a full decomposition of the suginome reagent in methanol. So that was a tedious parameters to control. So here is the scope, yields, linear branch ratio, which are pretty okay. We did also the reaction on more fancy substrate. What is interesting is that we can carry out the reaction with ferrocene, which is a redox active substrate, but the yield is pretty excellent, and we have a good branch and linear ratio. We also did the reaction of other substrate, and yields were okay. Then we still have an interest in organofluorine chemistry, so we were wondering if we could access to this allyl silane or an allyl borane. Sorry, there is a mistake here. It should be a borane by radical addition on this peculiar olefin, which upon fluoride elimination might give birth to this very synthetically useful allyl silane and borane. So we developed the reaction conditions, which are pretty close to the one we developed before. And for the borylation, here are some examples of the reaction scope. Yields are pretty okay. Usually it's a matter of purification because allyl borane might be a bit difficult to purify in silica gel, so you have to be very quick. So that will explain some low yield, for instance, in that case. Here are some examples with indole as well. We did it also with the suginome reagent. We had to tune a little bit the condition to use a platinum cathode, still a mixture of acetonitrile and methanol. And here are some examples from the scope. This one I do like it very much because this is tetrasubstituted olefin, so it could be very, very useful for making more elaborated fluorinated compound. So then we were interested in developing the flow condition, because for electrochemistry you need to use the flow to scale up the reaction, because this is a reaction that proceeds at the surface of the electrodes. So if you want to increase the scale, you need to increase the size of the electrodes. So when it's stainless steel, it could be okay. You can go up to 1 or 2 meters square of stainless steel. It's cheap, but when you have a platinum electrodes, quickly you increase the cost of the process, and of course it's impossible to do the reaction on large scale. So flow is basically the key to scale up this reaction. So we carried out the reaction using the Vaportec reactor. So this is a 0.6 milliliters reactor. We did it for the borylation. So we had to tune drastically the condition to change current intensity and also the flow. So the flow was a key parameters, and for the borylation we got 74% yield, but this is not the most important parameters in flow. The yield does not mean anything in flow. The most important parameters is the productivity. So basically the amount that you can produce per liter of reactor and per hour. Okay, and here we are close to 0.7 kilograms per liter and per hour, which is a good productivity because you can easily imagine to parallelize your reactor. Okay, this is very small reactor. It's basically like my hand, so you can have a lot of reactor that you can add in parallel, and you can quickly increase the scale of your reaction at very low cost. For silylation, the productivity was a little bit lower, 0.5 kilograms per liter per hour, but it's still acceptable, and you can produce a large amount of compounds if you really want to do. So now let me just talk about something that we recently developed. So could we, upon the same concept, forge alanine silane? So by using propergyl substrate, could we get access to this very synthetically useful compound? So that was the project that I gave to Ting Ting, and she did it. By using propergyl acetate, she checked carefully the electrodes, and it's again stainless steel electrodes. She tuned the electrolytes, so ammonium chloride, 30 milliamp, and the charge was adjusted depending on the substrate. Same reaction, same solvent mixture. We developed this, the synthesis of this alanine silane. So here are some examples of the scope. So very simple alanine silane with an aromatic group with some substituent. The yields were okay. We have been able also to use some heteroaromatics. So what was surprising is that most of these alanine silane are unknown. So that was a big surprise for us, but most of them are unknown. We also extended it to tri-substituted alanine silane, di-substituted with alkyl chain, with this olefin, cyclopropane, sulfur, but also some tri-substituted alanine silane, which can be very useful to build up more complex molecules. So with the ether, you can do a lot of chemistry. You have this fancy substrate, so that was pretty interesting. So we did some mechanistic study, and first we demonstrated that we have a retention of configuration. So the reaction is highly enantiospecific. So we started from 99.5 to 0.5, and we got the allene as enantiomer species. We did some CV. So we used the B2Pin2 because what I did not mention is that we extended the reaction to B2Pin2. It's not fully, it's not as efficient, but we did it. So we have this oxidation wave. It's a little bit dirty, but basically this is the oxidation wave of the mixture of B2Pin2 and sodium methoxide. And we mix it with the alkyne, and we got barely the same behavior here with a little bit lower oxidation. So we have an oxidative process. And we studied a lot the mechanism, and this is what we suggested. Like the other project, we generated sodium methoxide, formation of the borate, of course oxidation, generation of the radical. But here is the most puzzling part of the mechanism. So the radical might add to the alkyne to generate this vinyl radical, which is very high in energy, and then we have two possible pathways. So first, the extrusion of this radical here from the allene, we generate this radical, which is extremely stable. It cannot decarboxylate. You know, you cannot extrude CO2 from this radical. The half-life time is pretty long, so it can be reduced at the cathode to generate the anion, and then we might get the decarboxylation and the formation of the methoxide. Okay, so this is one pathway. The other one, which is inspired from the phosphonate elimination, so from the phosphate elimination, you might get formation of this radical cation here, and then upon reduction, you might go to the allene and to generate the methoxide. But actually, since we have a retention of configuration when we use enantiopure compounds, this pathway might be probably the most suitable one. But this is still a puzzling step in the mechanism. We don't really know how to explain it yet. We probably have to make some calculation, but it might take time. So now let me finish with the most important slide. So I would like to thank these guys for doing the chemistry. So Mo, Tony, and Ting Ting for carried out electrosynthesis. So this is pretty difficult for them because that was a surprise. They arrived in the lab, they expected to do something else, but they get the electrosynthetic machine in hand and they had to do it. So they were really good for that. I would also like to thank Ming Bing for all the work he did on copper photocatalysis. That guy had the magic hands for doing the complex, so that was great. I would also like to thank all the other collaborators, so Xavier, Philippe, and Mathieu for supervising all this project, and also the financial support. We cannot do any chemistry without money, so this is the funding involved in this project and the other financial support for helping us. And of course, I would like to warmly thank you for your kind attention, and I will be more than happy to answer to your question. Thank you.
Hi, Tom. So, very nice talk and interesting chemistry. So, I have a question relevant to this deuterium transfer when you use the acetonitrile water mixture. Because in your reaction mixture, if I see it, you do have a diisopropylethylamine, right? When you have a diisopropylethylamine in the presence of water, okay, under photoirradiation, so what happens is it forms a diisopropyl ethyl ammonium cation.
Actually, I think you're talking about the mirror borylation?
Yes, the copper.
This one?
Yeah.
This one we never carried out any.
Not this one, where you showed the.
Yes, I see.
Yeah, if you look at it, your reaction condition, so you do have a diisopropylethylamine, right?
No, we don't in that case.
In that case, okay.
We're using, in the standard condition, we are using potassium carbonate.
Okay.
So, but it's exactly the same concept. So we need to get the base to introduce hydroxide on the boron. Mm-hmm. Okay, because it's, in this case, potassium carbonate, I'll try to find the condition, yes. Potassium carbonate, you know, it's basic enough to generate hydroxide in the presence of B2Pin2. Okay, because this is a Lewis acid, the proton is more acidic. No, we don't. Actually, if you use the amine, you move on a reductive process, not an oxidative process.
Fantastic talk, Thomas, and really explained a lot of nice results. So I just want to know with copper and the boron radical you are mentioning, or silicon radical, is it a free radical, or I believe it's maybe connected, or with the copper? There
is no interaction with copper, but this is something that it's I should drastically change my slides because I'm drawing the boron radical without anything,
Yeah.
you know. But basically, it's ligated with a solvent.
Solvent.
Okay, so acetonitride is around, or the base is around. Otherwise, it's highly unstable. So it should be a ligated boryl radical. But for the sake of clarity, I rated it. So I omitted the ligand on the boryl radical. Otherwise, it's
Okay.
tough to read. No, of course, there is always something around the boron. Okay, a Lewis base is connected.
So regarding your stability of the
We checked the structure of the copper catalyst by enamel under the reaction conditions. So we did not irradiate it first, because at that time we didn't have the lamp in the enamel. Now we have it, so we can probably do it. But the structure doesn't change. Yeah. On phosphorus enamel there is no change. So the complex survived to the reaction and it's intact at the end. Of course, we did not recover it because it's very complicated. We cannot get it by flash, but no, it's highly stable.
Yeah, and regarding the stability of these copper-boron bonds under electrochemical conditions, so we know that they are very unstable under oxidative condition. So are they really stable? Like for a
The boron?
yeah, no, carbon-boron bond.
Oh yes, it's stable in the case of the only case where it's not stable is for when you get the alanine borane. Alanine borane is highly unstable. So usually we have very low yields, but we added the substrate under the electrochemical condition, and we have decomposition. Okay, so for aromatic alkyl, vinyl it's fine, but alanine it's the most complicated. Allyl borane it's still okay, but because we have the 2-fluorine, which are very important for the stability. Otherwise you cannot purify them. But the less stable were really the alanine borane.
Just one small final question about the instead of bipin. Okay, if you replace pinacol with the boronic acid, BOH, so
doesn't work
because something it can really different horizon. Yeah.
What
we can do a lot of nice chemistry after that.
No, we can't. What we can do is to introduce a bidan, because when you have a bipin bidan, you know the bipin is more acidic than the bidan, so the OH goes to the bipin, and when you cleave the BB bond, of course you generate the bidan radical. We can do that, but sometimes the reactivity is very different. It's less nucleophilic, so yeah, the reactivity change a lot. That's why we usually use bipin, B2pin2, and for the bipin silane, probably you notice it, but it's always dimethylphenyl. So the only trick is because they are extremely difficult to make, this boron silane, and that one is commercially available and the quality is fine. So that's why we are using only this one.
Get the absolute configuration of the allyl silane.
We don't know what is it.
Because it would maybe give information of what's happening.
But I think it's some kind of SN2 process, you kick it out.
Okay.
So this is our assumption. So we have a lot of questions.
Yeah.
So.
Thanks, Thomas. Nice talk. So, also a question on the mechanism here. So, if you you generate a carbon ion, have you tried to trap it with other electrophile other than water?
We tried a lot. At the beginning, we wanted to do borylation and introduce something.
With a radical or with a cation?
Yeah, but the H transfer is extremely fast, and that's why now we think it's an intramolecular process. The bipin is connected with water or with the OH, and then we have an intramolecular H transfer, and we cannot compete. So
and you are still not sure 100% whether it's HAT or H+.
I think it's HAT.
Okay.
It's really an intramolecular HAT because when you coordinate the water with one borane, so if you take just a boron, water, so this is a work from Wood and Renault, the BDE of water decrease a lot.
Okay.
You have a Lewis acid, so basically the OH bond is weaker, so the BDE is also weaker.
So to prove further this, is it possible to remove the water and use a catalytic amount of hydroxide and then add another HAT reagent to see?
We didn't try it, but water was extremely important.
Okay.
Actually, we did the reaction in pure acetonitride, or it does not work well. It's very messy. So we need the water, and that's really something. In all the reaction, we need water, but many radical reactions need water. It's a polarity effect, I think. So it's very difficult to remove it We can do the reaction with water, but not with oxygen. Oxygen is killing all the processes.
Long live India and France friendship.